comparison between boron and carbon. Comparison between boron and carbon. Okay. Boron is a member of group 13 and carbon is a member of group 14. Okay. Boron is a member of group 13. Group 13. Okay. And carbon is a member of group 14. Okay. Similarities. This similarity is of a carbon and boron are so you can show first point. Both are non-metals. Both are non-metals. Both are non-metals. Second point. Both form acidic oxides. Both form acidic oxide. Both form acidic oxides. Okay. B2O3 CO2. B2O3 CO2. Okay. Third point. Both exhibit allotropy. Both exhibit allotropy. Both exhibit allotropy. 14 point. They combine with metals to form borides and carbides respectively. They combine with metals to form borides and carbides respectively. Okay. 15 point. Both form hydrides. Both form hydrides. Carbon hydrides are known as hydrocarbons. Carbon hydrides are known as hydrocarbons. Whereas boron hydrides are known as boranes. Boron hydrides, whereas boron hydrides are known as boranes. Okay. 6 point. Point 6. Both possesses a small atomic volume. Both possesses a small atomic volume. Okay. 7 point. Point 7. Both form oxides. Both form oxides like carbon dioxide CO2, carbon dioxide and boron trioxide B2O3, which are acidic, which are acidic. Okay. Next, dissimilarities. This is the similarities. Next is dissimilarities. Okay. Dissimilarities. Next point, dissimilarities between carbon and boron. Dissimilarities between boron and carbon. Dissimilarities between boron and carbon. Okay. Dissimilarities between boron and carbon. The dissimilarities between boron and carbon, and so you can show this. First, boron does not conduct electricity. Boron does not conduct electricity. Boron does not conduct electricity, whereas graphite and allotrope. Whereas graphite and allotrope. Graphite and allotrope. Graphite and allotrope. Okay. Graphite and allotrope of carbon. Allotrope of carbon. Graphite is allotrope of carbon. Okay. Allotrope of carbon is a good conductor. Good conductor of electricity. Okay. Second point, boron reacts with alkalis to form borates. Boron reacts to alkalis. Okay. Boron reacts to alkalis to form borates, but carbon does not react with alkalis. Okay. With alkalis. Third point, boron has a definite melting point. Boron has a definite melting point. Whereas melting point of carbon is not known. Whereas melting point of carbon is not known. Okay. Fourth point. Carbon atoms can be linked with each other. Carbon atoms can be linked can be linked, carbon atom can be linked with each other, with each other, to form long chain compounds, to form long chain compound, long chain compound, okay, long chain compound, okay. Carbon atoms can be linked with each other to form long chain compound, but boron does not possess this property. Boron does not possess this property, okay, this property. Fifth point, carbon tetrachloride is a liquid. CCl4 is a liquid. Carbon tetrachloride is a liquid, not decomposed by water. Not decomposed by water. Not decomposed by water. Whereas BCl4, boron tetra, BCl13 is a gas hydrolyzed by water. BCl13 is a gas hydrolyzed by water. Hydrolyzed by water. Okay. BCl3 plus 3H2O, that is S3BO3 plus 3HCl. Okay. Elements of group 14 carbon family. Okay. Carbon, silicon, germanium, tin and lead are the member of group 14 of the periodic table. Okay. Carbon, silicon, germanium, tin, stainless, tin and lead are the member of group 14, okay, are the member of group 14 of the periodic table. These are normal elements. Carbon and silicon are non-metals. Germanium is metals. Germanium is a metallite, while tin and lead metals. Okay. Carbon and silicon are non-metal. Carbon and silicon are non-metal. Okay. Carbon and silicon are non-metals. Germanium is metallite. Germanium is metallized. Germanium is metallite. Okay. While tin and lead metals. Tin and lead metals. Okay. The metallic to increasingly metallic character becomes evident as we go down from the carbon to lead. Carbon possesses properties little in common with those of the other elements. This is due to its small size and high ionization energy value. Okay. The group occupies the middle of the periodic table, forming a link between more electropositive elements of group first to group 13 and the more electronegativity elements of group 15 to group 17. 5 to 17, okay? Electronic configuration. Electronic configuration. Electronic configuration. Electronic configuration, okay? Electronic configuration. Elements. Elements. Symbol. Element. Symbol. Atomic number. Atomic number. Element symbol. Atomic number. Element symbol. Atomic number. Electronic configuration. Electronic configuration. Electronic configuration. Electronic configuration. Electronic configuration of outermost shell. Electronic configuration. Electronic configuration of outer shell. Okay? Elements carbon. Elements carbon. Symbol C. Symbol C. Electronic atomic number 6. Atomic number 6. Electronic configuration 1s2, 2s2, 2p2, and outermost configuration, electronic configuration of outer shell 2s2, 2p2. Next point, next elements. Silicon. Next element, silicon. Symbol Si and atomic number 14. And electronic vinyas, electronic configuration 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, 4s2, 4p2. Okay? And 1s2, 2s2, 2p6, and 3s2, 3p6. And electronic configuration of outer cell, 3s2, 3p6. Next element is germanium. Next element is germanium, and symbol Ge, and atomic number 32, and electronic configuration 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, and 4s2, 4p2. Okay? Electronic configuration of outermost cell 4s2, 4p2. Okay? Next. And after germanium, next is tin. And symbol Sn, and atomic number 50. Electronic configuration 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, and 4s2, 4p6, 4d10, 5s2, 5p2. And outermost electron configuration of outer shell is 5s2, 5s2 5p2. Okay, next point. Next point. After tin, lead. After tin, lead. And symbol Pb. And atomic number 82. Electronic configuration 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, and 4s2, 4p6, 4d10, 4f14, 5s2, 5p6, 5d10, 6s2, 6p2, and electronic configuration 6s2, 6p2. Okay. The outermost electronic configuration is ns2, np2. Hence, these are p-block elements. All elements contain 4 electrons in their outermost orbit. Carbon and silicon have only electrons in s and p orbitals, while germanium, tin, and lead also contain fully filled d orbitals in a penultimate. Okay, in penultimate orbit. Okay. Next, physical property of group of 40 elements. Physical property of group 40 elements. Okay. 1 minute. Physical property of group 14 elements. Okay. Properties. Physical properties. Physical properties of elements. Physical properties of elements. And next is atomic number. Atomic number. Next is atomic number. Atomic number. Atomic weight. Atomic weight. Atomic weight. And after that, atomic radii. Atomic radii in angstrom. And next is ionic radii. Ionic radii m plus 1 in angstrom. And next is melting point in degrees Celsius. And density. Next is density in gram per semi-cube. And after density, next is electronegativity. And after electronegativity, ionization energy, kilojoule per mole. Okay, kilojoule per mole. First, second, third, and fourth. second ionization energy, third ionization energy, and fourth ionization energy. Okay, fourth ionization energy. Okay, first element carbon, atomic number 6 and atomic weight 12.1, atomic radii 0.77, ionic radii, okay, and ionic radii is a 0.77, atomic radii 0.77, and ionic radii is 0.15, and melting point 3527, and density 4327, and density gram per semi cube. Boiling point, this is a melting point of 3527, this is a melting point, sorry, this is melting point, and boiling point, and the second is, and boiling point 4327, boiling point 4327, 3.52, density 3.52, okay, and electronegativity 2.5, oxidation state 2.5, and this is oxidation state is plus 4, and first ionization energy 1086, and 2350, and 4620, and 6230. Okay, next element silicon, okay, next element silicon, and atomic number 14, and atomic weight 28.08, and atomic radii 1.17, and ionic radii 0.41, and melting point 1414, and boiling point 2680. Okay, and density 2.33, electronegativity 1.9, and oxidation state plus 4. Okay, and first ionization energy 786, second is 1580, and third is 3230, and fourth is 4360. Okay, third elements, germanium, atomic number 32, and atomic weight 72.6, and atomic radii 1.22, ionic radii 0.53, and melting point 959, and boiling point 2830, and density 5.33, and electronegativity 1.8, oxidation state plus 2, and first ionization energy, melting point 959, and boiling point 2830, and density 5.33, and electronegativity 1.8, oxidation state plus 2, and first ionization energy 762, second ionization energy 1540, and third ionization energy 3300, and fourth ionization energy 4410, 4410, and next, after germanium, stainless, that means tin. Tin atomic number 50, atomic weight 118.89, and atomic radii 1.41, ionic radii 0.71, and melting point 232, boiling point 2270, and density 7.3, electronegativity 1.8, and oxidation state plus 2. First ionization energy 709, second ionization energy 1410, third ionization energy 2940, and fourth ionization energy 3930. Okay, and next is lead. Okay, next is lead. Atomic number 82, atomic weight 207.19, atomic radii 1.54, ionic radii 0.84, and melting point 327.5, and boiling point 17.25, and density 11.34, and electronegativity 1.8, and oxidation state plus 2 plus 4, and first ionization energy 745, second ionization energy 1450, third ionization energy 2080, and fourth ionization energy 4080. Okay, the general physical characteristics is discussed as follows. First is occurrence. Okay, first is occurrence. Okay, all elements found in nature in excess except all elements found in nature in excess except germanium, which is a rare element, okay. All elements found in nature in excess except germanium, which is a rare element. Okay. Carbon is the main constituent of the organic matter. All elements found in nature in excess except germanium, which is a rare element. Carbon is the main constituent. Carbon is the main constituent. Carbon is the main constituent of all organic matter. Okay, and plants wise. Plants while silicon is the main constituent. Silicon is the main constituent. Silicon is the main constituent of inorganic matter like minerals. Okay. Second point, metallic nature. Okay. Carbon is non-metal. Silicon, germanium are semi-metals. Metallite. Silicon, germanium are semi-metals. Silicon, germanium are semi-metals. Metallite and tin and lead are metals. Okay. The non-metallic property has the order. The non-metallic properties has the order. The non-metallic property has the order. Carbon is greater than silicon, is greater than germanium, is greater than tin, is greater than lead. Okay. Carbon is non-metal, silicon, germanium, semi-metals, metallite and tin and lead are metals. The non-metallic property has the order. Carbon is greater than silicon, is greater than germanium, is greater than stainless steel, is greater than lead. Okay. Then the metallic property has the order. The metallic property has the order. Carbon is less than silicon, is less than germanium, is less than stainless steel, is less than lead. Or the metallic property is the lead is greater than steel, is greater than germanium, is greater than silicon, then the greater than carbon. Okay. And carbons. Okay. Then atomic radii. Next is atomic radii. Okay. Atomic radii. Okay. Atomic radii. The atomic radii of group 14 elements are smaller than the atomic radii of group 13 elements. Okay. The atomic radii of group 14 the atomic radii of group 14 elements are smaller than the atomic radii of group 13 elements. The order of atomic radii is carbon is less than silicon, is less than germanium, is less than tin, is less than lead. Okay. The atomic radii increases on moving down the group. The atomic radii increases the atomic radii increases, the atomic radii increases and moving down the group, 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 and moving down the group due to increase in orbit number, due to increase in orbit number, okay, due to increase in orbit numbers, okay, and the difference in radii of silicon and germanium is less, and difference in radii, radius difference in radius of silicon and germanium is less due to d block contraction, and between tin and lead is due to lanthanide contraction effect, is due to lanthanide contraction effect, carbon, silicon, germanium, tin and lead. Carbon is 0.77, silicon is 1.17, germanium is 1.22, tin is 1.41 and lead is 1.54 angstrom. Okay, atomic radii. The atomic radii of group 14 elements are smaller than atomic radii of group 13 elements. The order of atomic radii is carbon is less than silicon, is less than germanium, is less than tin, is less than lead. The atomic radius increases and moving down the group due to increased orbit number. The difference in radius of silicon and germanium is less due to d block contraction, and between tin and lead is due to lanthanide contraction effect. Okay, fourth point. Point 4, atomic volume. Okay, next, atomic volume. As the atomic radius increases gradually, so does the atomic volume, as shown below. As the atomic radius increases gradually, as the atomic volume increases gradually, so does the atomic volume, I show carbon, silicon, germanium, tin, lead. Atomic volume of carbon 5.0, atomic volume of silicon is 11.4, atomic volume of germanium is 13.6, and atomic volume of tin is 16.3, atomic volume of lead is 18.27 in cc. Okay, melting and boiling point, 5 points. Melting point and boiling point. Melting point and boiling point. Okay. The element of group 14 can form 4 covalent bonds. Thus, there are strong binding forces between the atoms Hence, the melting and boiling point of group 14 elements are much higher than group 13 elements. And moving down the group, carbon and lead metallic character increases. Consequently, both melting and boiling point value decreases. Okay. Okay. The melting and boiling point of group 14 elements, the melting point and boiling point of group 14 of group 14 elements are much higher. Group 14 elements are much higher than group 13 elements. Then group 13 elements. Okay. And moving down the group, from carbon to lead. From carbon to lead, metallic character increases. Metallic character increases. Consequently, both melting point and boiling point values decreases. Okay. Decreases. Melting and boiling point. The element of group 14 can be formed of 4 covalent bonds. Thus, there are strong binding forces between the atoms. Hence, the melting and boiling points of group 14 elements are much higher than group 13 elements. And moving down the group from carbon to lead, metallic character increases. Consequently, both melting and boiling point values decreases. Okay. Next point. Point number 6. Ionization potential. 6 point. Ionization potential. Okay. Ionization potential. The ionization potential value decreases gradually with increase in atomic number. Ionization potential of lead is greater than that of tin due to higher effective nuclear charge of lead. Okay. Ionization potential value decreases gradually. The ionization potential value decreases gradually with increase in atomic number. Ionization potential of lead is greater than that of tin due to higher effective nuclear charge. Higher effective nuclear charge of lead. Okay. Ionization potential. The ionization potential value decreases gradually with increase in atomic number. Okay? Ionization potential of lead is greater than that of tin due to higher effective nuclear charge of lead. Okay, the ionization potential value decreases gradually with increase in atomic number. Ionization potential of lead is greater than that of tin due to higher effective nuclear charge of lead. Okay, 7.7. Point number 7.7. Okay, electropositive properties. Electropositive properties. Electropositive properties. Electropositive properties. Electropositive properties. Okay, and moving down the group from carbon to lead, ionization energy decreases, consequently electropositive character increases. Okay, and moving down the group, and moving down the group, from carbon to lead, and moving down the group from carbon to lead, ionization energy decreases. Ionization energy decreases, consequently electropositive character increases. Consequently electropositive character increases. Okay, and moving down the group from carbon to lead, ionization energy decreases, and consequently electropositive character increases. Electronegativity. Next point, point 8, electronegativity. Next point, electronegativity. Okay, electronegativity. Next point, electronegativity. Okay, electronegativity. Next point, electronegativity. Okay, and moving down the group from carbon to lead, ionization energy decreases, consequently electropositive character increases, and moving down the group, electronegativity decreases due to increase in the size of atom and screening effect of inner shell. Carbon has the maximum and lead has the minimum value of electronegativity. Okay, and moving down the group, electronegativity decreases. Electronegativity, and moving down the group, electronegativity decreases due to increase in the size of atom and screening effect of the inner shell Carbon has the maximum carbon has the maximum, carbon has the maximum, and lead has the minimum. Lead has the minimum value of electronegativity. Okay. Next, allotropy. Next is allotropy. Allotropy. Okay. All of these elements show allotropy except lead. Carbon exists in two crystalline forms, diamond and graphite, and in several amorphous forms. Silicon occurs in crystalline and amorphous forms. Germanium in two crystalline forms. Tin occurs in three allotropic forms: gray, white, and rhombic tin. Gray, white, and rhombic tin. Okay. Then allotropy. All of these elements show allotropy except lead. All of these elements, all of these elements show allotropy except lead. Carbon exists in two crystalline forms. Two crystalline forms. First is diamond. And second is graphite. Okay. And in several amorphous forms. And in several amorphous forms. Okay. Silicon occurs in crystalline. Silicon occurs in crystalline and amorphous. Forms. Germanium in two crystalline forms. Okay. Germanium in two crystalline forms, and tin occurs in three allotropic forms. That is gray, white, and rhombic tin. Okay. 10 points. Point 10. Catenation. Okay. 10 points. Catenation. Okay. Catenation. 10 point. Catenation. Okay. Carbon has been tendency of forming long chains by self-linking. This property is known as catenation. Silicon forms chain to a limited extent. The catenation property decreases in the order of given reason. Okay. So you can write carbon has a tendency of forming long chains. Carbon has the tendency of forming long chains. Long chains by self-linking. by self-linking. Okay. Carbon has the tendency of forming long chains by self-linking. Okay. And this property is known as catenation. This property is known as catenation. Known as catenation. Silicon forms chain to a limited extent. Silicon forms chain silicon forms chain to a limited extent. Okay. To a limited extent. Silicon forms to a limited extent. The catenation property decreases in the order of given carbon is less than silicon is less than germanium is less than stainless steel is less than lead. Okay, is less than lead. Okay, catenation property depends on the bond energy. The catenation property of carbon is the maximum because carbon bond energy is 82 kilocalorie and is highest among silicon, germanium, tin, and lead. Due to catenation property, carbon forms a large number of organic compounds. Okay. Catenation property depends on bond energy. Catenation properties depends on bond energy. Depends on bond energy. The catenation property of carbon is the catenation property of carbon is the catenation property of carbon. 1 minute. The catenation property of carbon is the maximum because carbon bond energy okay. Property carbon is the maximum because carbon bond energy is 82 kilocalorie and is highest among silicon, germanium, tin, and lead. Okay, lead. Due to catenation property, carbon forms large number of organic compounds. Carbon. Okay, carbon. Okay, and bond energy. Carbon bond energy 83, silicon bond energy 53, germanium bond energy 40, and tin bond energy 37 kilo calorie. Okay. Then as silicon oxygen bond energy is high 106 kilocalorie. Silicon has the property of forming complex silicates by forming silicon oxygen linkage. Okay. And you can show as silicon oxygen bond energy bond energy is high, approximately 106 kilocalorie. Silicon has the property of forming complex silicates by forming silicon oxygen linkage. Okay. And the complex silicates are formed by sharing of oxygen of SiO4 tetrahedral. Silicon and lead have no such property. Okay. Next point, oxidation state. 11 point, oxidation states. Okay. Oxidation state. Next is oxidation state. Okay. Oxidation state. What is oxidation state? +2 and +4 oxidation states are common to all. Okay. +4 oxidation state is due to participation of NH2NP2 electrons, and +2 state is due to participation of only NP2 electrons. Due to inert pair effect, stability of +4 oxidation state decreases with increase in atomic number in the group of +2 oxidation state increases. For carbon, +2 oxidation state is less stable, but for lead, +2 oxidation state is more stable. So carbon also shows variable oxidation states. In addition to +4 oxidation state, carbon shows 2, 4, 2, 1, 0, +1, +2 oxidation states in compounds such as CH4, C2H4, C2H2, and C12H22 compounds such as carbides. Okay, etc. Inert pair effect. But you can write something about oxidation state. Okay. +2 and +4 oxidation state are common to all. +2 and +4 oxidation states are common for all. Common to all, and +4 oxidation state is due to participation of +4 oxidation state is due to participation of NH2NP2 electrons. Okay. Electrons and +2 state is due to participation of, and +2 state is due to participation of participation of only np2 electrons, okay, np2 electrons. Due to inert pair effect is that due to inert pair effect inert pair effect, okay. Stability of +4 oxidation state decreases with increase in atomic number in the group, and +2 oxidation state increases, okay. +4 oxidation state decreases, +2 oxidation state increases. For carbon, +2 oxidation state is less stable, but lead +2 oxidation state is more stable, okay. Carbon also shows variable oxidation state. In addition to +4 oxidation state, carbon shows -4, -2, -1, 0, +1, +2 oxidation state in compounds such as methane, C2H4, C2H2, ethene, okay, ethine, and C12H22, okay, and O11, and H2CO2, H2C2O4, carbon monoxide respectively. Carbon also shows negative oxidation state in some compounds such as carbides, okay. And next is inert pair effect. Next is 12 inert pair effect. Inert pair effect, okay. Next is inert pair effect. Inert pair effect. Oxidation state of heavier elements of P block in group 14. Germanium, silicon, and lead have oxidation number +4 and +2 also, which is more stable towards germanium to lead. This is due to presence of inert pair effect. Inert pair effect is shown by the last three elements, germanium, silicon, and lead, in increasing extent. Hence, these elements have a tendency to form M+2 ions as well as M+4 ions. This effect is not predominant in germanium. Hence its compounds in +2 oxidation state are unstable and are easily oxide to the compounds in which germanium is in +4 oxidation state. Thus germanium compounds are strong reducing agent, okay. Strong reducing agent. 1 minute. Inert pair effect. The oxidation state of a heavier element the oxidation state of heavier elements of P block, in group 14 is that germanium, silicon, and lead have is that germanium, silicon, and lead have oxidation number +4 and +2, also, which is more stable, more stable, which is more stable towards germanium to lead, towards germanium to lead. This is due to presence of inert pair effect. Due to presence of inert pair effect. Presence of inert pair effect. Due to presence of inert pair effect. Okay? Inert pair effect is shown by the last three elements. Inert pair effect in Inert pair effect is shown by the last three elements. Germanium, tin, and lead. Germanium, tin, and lead in increasing extent. Okay, in increasing extent. Okay, and hence these elements have a tendency to form. M+2 ion. Okay, M+2 ion as well as M+4 ion. M+4 ion. Okay, and this effect is not predominant in germanium, hence its compound in +2 oxidation state are unstable and are easily oxidized to the compounds in which germanium is in +4 oxidation state. Thus germanium compounds are strong reducing agent. Okay, then germanium unstable, germanium unstable and oxidation germanium 4 stable and +2 electron. Okay, tin and lead forms Sn+2 and lead +2 ions. Tin and lead form Sn+2 and Pb+2 ions. Okay, which are stable and more common than tin+4 and lead+4 ions. In tin, the NH2 electron pair is unpaired, less easily to give Sn4. Okay, then Sn second oxidation Sn4 less stable plus 2 electron. Okay, hence tin second compounds are normal reducing agent. Hence tin second compounds are normal reducing agents. Okay, normal reducing agents. In lead second, the NH2 electron pair is not unpaired easily to give lead fourth, hence lead second is stable and lead 4 unstable. Lead 4 lead 4 less stable, unstable, 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 and plus 2 electron reduction, reduction, lead second, and more stable, more stable, more stable, okay, more stable. Hence, lead fourth compounds are strong oxidation state. Lead fourth strong oxidation state, oxidizing agent, strong oxidizing agent. The not pair effect in lead second is thus maximum more. According to Fajans rule, smaller the cations, greater is the tendency to form covalent compounds. The tin fourth and lead fourth ions have much smaller radii than tin second and lead second ions. Thus, Sn4 plus 4 and lead plus 4 compounds of tetravalent tin and lead are more covalent in nature. Compounds of bivalent tin plus 4 and lead plus 2, tin plus 2 and lead plus 2 are more ionic than their tetravalent states. Okay, nature of bond. Next, nature of bond. Okay, nature of bonds. Okay, nature of bonds. The elements of group 14 are tetravalent in nature. Okay, they normally do not form M plus 4 ions as their ionization potential is very high. They also do not form M4 negative ions as they have low electronegativity. They show covalency of 4 by acquiring sp3 hybridization, which results in tetrahedral structure. Okay, the elements of group 14 are tetravalent in nature. The element of group 14 are tetravalent in nature. Tetravalent in nature. They normally do not form M plus 2 ions as their ionization potentials are the elements of group 14 are tetravalents in nature. Okay, they normally do not form M plus 2 ions. They do not normally form M minus 4 ions. M minus 4 ions as their ionization potential are very high. Ionization potential are very high. They also do not form plus 4 ions. Okay, they normally do not form plus 4 ions as their ionization potential are very high, and they also do not form M4 negative ions. M negative 4 ions as they have low electronegativity. They have low electronegativity, electronegativity. Okay, they show a covalency of 4 by acquiring sp3 hybridization, which results of tetrahedral structures. Okay, ground state ns2 np2, that is plus 2 oxidation state, plus 2 oxidation state, excited state, ns1 p x1 py1 pz1. Okay, that is sp3 hybridization, sp3 hybridization and plus 4 oxidation state, plus 4 oxidation state. Okay, in plus 4 oxidation state of all elements have covalent bond: carbon dioxide, silicon dioxide, germanium dioxide, tin dioxide, lead dioxide, and essential for lead tetrachloride, tin tetrachloride, etc. All are covalent in plus 2 state. Okay, carbon monoxide is covalent, but germanium plus 2, stainless plus 2, lead plus 2 are ionic. However, there is a considerable covalent character in compounds of plus 2 state of tin and lead. The hydrolysis of state in plus 4 plus 2 states is evidence for covalent character in compounds. Alkaline earth carbides such as CaC2 calcium carbide has a carbon plus 2 and carbon to C2 minus calcium plus 2 and C2 minus 2 unit and have minus 1 oxidation state. Thus calcium carbide is ionic in nature. Okay, next, chemical properties of group 14 elements. Chemical properties of group 14 elements. Chemical properties of group 14 elements. Okay.